All right, welcome AP Chemist. This is Ralston Valley High School's AP Chemistry Lecture Series, Chapter 15, in which we will be discussing complex ion equilibria, lecture number 5. Let's get started. All right, here we go, discussing complex ions, species which you have actually met during first semester. Many of you have completed a lab in which we investigated the formation of complex ions. A real brief bit of background here to refamiliarize yourself with the idea. Recall a complex ion is a charged species that is generally made up of a central metal cation, which is bonded to one or more ligands. And recall, a ligand is a species which can donate a pair of electrons to form a coordinate covalent bond. Now, with this definition in mind, you may remember forming complex ions with the copper-2 nitrate solution to which we added excess concentrated ammonia. The copper-2 nitrate solution contains copper-2 ions, and the positive charge on those copper-2 ions, being positive, is likely going to attract negative charges anywhere within the solution. So upon the addition of excess ammonia, if we draw a real quick Lewis dot structure here, you see that that ammonia molecule has a lone pair of electrons that is a negatively charged site on each ammonia molecule. And therefore, that ammonia molecule can act as a Lewis base, donating the electron pair, in doing so, forming a coordinate covalent bond to the copper-2 ion. Now, because the ammonia molecule itself is neutral overall, the addition of one ligand, that is one ammonia molecule, to the copper-2 ion doesn't change the overall net charge on the ion itself. Again, it still has a +2 charge that it began with. And as such, the copper-2 ion can continue to form these coordinate covalent bonds, attracting more and more ammonia molecules within the solution. And really, the defining factor here, which determines how many of those ligands will bond to the central copper-2 ion, isn't charge, as it would be in a traditional, like, say, ionic equation, but instead is really geometry. That is, how many of those ligands can we fit around the outside of this central cation. And you may remember, as a general rule of thumb from last semester, the number of ligands which tend to bond to the central metal cation is usually double the charge of the cation itself. And as such, in our system, as we see the copper-2 ion has a +2 charge, 4 of those ammonia molecules, 4 of our ligands, bond to the central metal cation, forming the complex ion CuNH3,4, which again collectively shares a +2 charge. Now, during first semester, we qualitatively investigated the formation of these metal cations. And if you remember from our lab, the evidence which we observed showing the formation of a metal cation was the redissolving of a precipitate which we had formed, indicating the formation of a more soluble species in solution. So during that lab, we again first precipitated out, say, like copper-2 carbonate from solution, and then once we had formed that copper-2 carbonate solution, the addition of excess ammonia caused the formation of the tetraamine copper-2 complex ion, which itself is more soluble in solution, and as such, it then underwent dissociation from the carbonate ions and then dissolved that precipitate into solution. Now, over the course of this conversation, we're going to look at complex ion formation from a more quantitative perspective. And the first thing we want to do is to recognize that the formation of complex ions is itself essentially going to be governed by the rules of equilibrium. So the process of forming a complex ion can be thought of as a sequence of individual steps. First, that central metal cation is going to attract one of those ligands and again form a coordinate covalent bond, forming an intermediate species. And again, we can continue to add those ligands one by one until we have seen the complete formation of our complex ion. So what I'd like to do here in this little table is to write up the equations which describe the stepwise formation of a complex ion. In this case, the tetraiodmercurate 2 complex ion, whose formula is Hgi4, 2 negative, from ions available in a solution which contains mercury 2 ions and iodide ions. So let's go ahead here and write an equation which describes that mercury 2 ion in solution picking up the first of those ligand ions, that is the iodide ion I1 negative. If I add Hg2 positive to I1 negative, the intermediate species which I form as a product of that reaction would have the formula HgI, whose charge would now be 1 positive. And I can continue this process again, adding more and more of those ligands as we go. The HgI 1 positive product that I formed in the first stepwise reaction will now become my reactant in a second reaction, in which it picks up another iodide ion, in this case now forming HgI2, and then we'll continue to add more and more iodides as we go here. The HgI2 product of the second reaction will become again a reactant in the third reaction, and if we pick up another iodide ion, that leaves me now with HgI3, who now has a 1 negative charge, as I've added 3 negatively charged iodides to the Hg2 positive that I originally started with. And then finally, one more time here, we'll go ahead and write the reaction in which HgI3, 1 negative, picks up an additional iodide, I1 negative, to form that product HgI4, 2 negative. Now, recognize here, folks, that in this sequence of steps, the overall reaction that describes here is really the sum of the individual steps themselves. So if we look at the first two reactions there, notice that the species HgI1 positive is a product of the first stepwise reaction and then is consumed in the second reaction, that is to say, it is an intermediate species. So I'm going to go ahead and cancel out that intermediate species here as I add these reactions together. And you notice I can cancel out my other intermediate species here of HgI2, as well as HgI3, 1 negative. And as such, if I sum those four reactions together, canceling out those intermediate species, the overall reaction that takes place here is Hg2 positive plus 4 I negative ions are reacting together to form that complex ion HgI4 with a -2 charge overall. Now, recall we discussed earlier that the formation of a complex ion itself is going to be governed by our rules of equilibrium. So I'm going to go ahead here, and for each of these four stepwise reactions, I'm going to write the K expression which governs the formation of the intermediate species and the formation of the final complex ion in the end. So let's go ahead here and write our initial K value here. I'm going to go ahead and label this one as K1 for the first stepwise reaction. As always, a K value is the ratio of the concentration of the products over the concentration of the reactants raised to the exponent powers of the coefficients from the balanced chemical equation. So the K expression for my first stepwise reaction here in the process of the formation of this complex ion would be the product there, which was HgI1 positive, the concentration thereof, divided by the concentration of that mercury 2 ion, Hg2 positive, times the concentration of the other reactant, I1 negative. So there's my first K expression. I'll call that K1. Let's repeat this process now for the K expressions of the remaining three stepwise reactions. For the second stepwise reaction, the product there is HgI2. So K2 here would be the concentration of HgI2 divided by my reactants, which for the second reaction was HgI1 positive times the concentration of I1 negative. We'll write a K3 now as well. For that third stepwise reaction, the product of the reaction was the ion HgI3, 1 negative. We'll divide that concentration by the concentration of the reactants, which is HgI2, times the concentration of I1 negative. And then last but not least, for the final stepwise reaction, the equilibrium constant K4 here would be the product of the concentration of HgI4, 2 negative, divided by the concentration of my reactants, HgI3, 1 negative, times I1 negative's concentration. So I've got the K expressions which govern each of these four individual stepwise reactions. And now we're going to do a little bit of math wizardry here. I'm going to go ahead and multiply together the product of K1 times K2 times K3 times K4. That is the product of the K values that govern each of the four individual stepwise reactions. And as I multiply these values together here, you'll notice something kind of magical happens, which very similarly relates to how we had canceled out the intermediate species in these stepwise reactions when we summed the overall reactions together. So notice here that the intermediate species, which was the product of my first stepwise reaction, that is HgI1 positive, shows up in the numerator of my first K expression and in the denominator of the second K expression. And as such, I can cancel out that species, HgI1 positive, and we can get rid of those intermediate species. Likewise, the product of the second reaction, that intermediate species HgI2, is in the numerator of K2 and in the denominator of K3, and as such, I'm going to cancel that one out as well. And same thing here for the species HgI3 1 negative. That intermediate species was the product of the third reaction, and as such, in the numerator of K3. I'm going to cancel out here because it also shows up in the denominator of K4. So now, having canceled out all of those intermediate species that show up both in the numerator and the denominator, the product of K1 times K2 times K3 times K4 ends up being here. In my numerator, I have the concentration of HgI4, 2 negative, divided by, in my denominator, I've got that mercury 2 ion, Hg2 positive, times the concentration of that iodide ion, which you'll notice here is going to be now raised to the 4th power. And as it turns out, that value we've just derived right there should look very, very familiar because that is the equilibrium constant for the overall reaction describing the formation of the complex ion. So long story short, what it really tells us here is if we can make an overall reaction by summing together individual stepwise reactions to yield an overall process, the K value of the overall expression would be the product of the K values of the individual stepwise reactions we use to make that overall process form. All right, so now that we understand this property in terms of the relationship between the equilibrium constants of each stepwise reaction and the overall equilibrium constant for the formation of the complex ion, we can now simply look up some data describing the K values of the individual stepwise reactions and use it to calculate the K value of the overall process. Looking up in some literature here, I find the K value of the first stepwise reaction here to be 3.2 times 10 to the third. K2, describing the formation of the second intermediate species there, has a K value of 1.7 times 10 to the fourth. The third K value of 1.9 times 10 to the fourth. And the fourth K value here, looking up, I find a value of 5.6 times 10 to the fifth. Now, first of all here, folks, notice that each of these individual K values is itself a large value of K, and as such, the formation of each subsequent intermediate species is a favorable process to occur. Now again, when I multiply all those K values together to find the overall value of K for this expression, I find that calculated value for the overall K of our expression to be about 5.8 times 10 to the 17th. So whereas each individual stepwise process was a highly favorable event, the overall K expression governing the formation of the complex ion itself is very, very favorable in terms of favoring the formation of products. So again, this would be an equilibrium that would say heavily favors the formation of products in our system. We can now use this understanding that the formation of the complex ion is highly favorable from an equilibrium perspective to explain then why the formation of a complex ion might allow a solute to become more soluble if we add a solution containing a ligand to a solute which itself is highly insoluble. So let's go ahead and see if we can apply this now to a solubility system on our next slide. All right, so on this slide here, we're going to look at how the formation of a complex ion might affect the solubility of a particular insoluble solute in solution. Have a look at the first reaction I've written here for you, which is the reaction describing the dissociation of a highly insoluble solute, that is silver chloride, AgCl. Upon dissociation, the silver chloride separates apart into the silver ion, Ag1 positive, and a chloride ion, Cl1 negative. And the equilibrium constant which governs this dissociation would in this case be a solubility product constant, that is Ksp, which I look up a value here of 1.6 times 10 to the negative 10th, again implying this is a highly insoluble solute in our solution. Now, again, you may recall that we could take a highly insoluble solute and add to it excess of concentrated solution of ammonia to cause that solute to redissolve back into the solution. And we're going to go ahead and show this here by looking now at the steps which govern the formation of a complex ion, that is the diamine silver complex ion AgNH3 2 1 positive. So in terms of two stepwise processes here, I'm going to give you a reaction that describes, first of all, when a silver ion in solution picks up a ligand molecule, which is an ammonia molecule, NH3, again by forming a coordinate covalent bond, using that lone pair of electrons on the nitrogen to form a bond to the silver ion. We would then form the intermediate species here, AgNH3, 1 positive. And the K value, which governs the formation of this intermediate species, is 2.1 times 10 to the third, again indicating that this is a highly favorable process within the solution. Now again, that silver ion, AgNH3 1 positive, can itself pick up another ligand molecule, and as we pick up another NH3 in solution, the product of that reaction would now be the formation of the ion AgNH3 with a 1 positive charge. That is the diamine silver complex ion. And the K which governs this equilibrium, I'm going to go ahead and label this one here K3 for the third reaction in our sequence here, has a value of 8.2 times 10 to the third. So we've got now K expressions which govern three individual stepwise processes which could be occurring within our solution. Now, what I want to do is I want to sum together these three reactions overall. And as I sum those reactions together, notice here that the silver ion Ag1 positive is formed as a product in the dissociation equation in the first reaction, but that silver ion is also consumed as a reactant in the second reaction here. So I'm going to go ahead and cancel those species out as they, again, are intermediates in the sum of our overall process. Likewise, that ion AgNH3 1 positive that is formed during the second reaction is itself consumed during the third reaction, and as such, again, is another intermediate species which I can cancel out. So the overall sum of these three stepwise reactions is silver chloride AgCl, my solid precipitate in solution, is going to combine together with two ammonia molecules, forming then the products here, which are AgNH3 1 positive, our diamine silver complex ion, and a chloride ion Cl negative. And note here that this overall reaction really describes the silver chloride dissolving into solution into separate ions. That is to say, it's becoming more soluble in solution as we sum these reactions together. And as you saw before, I can calculate the K value of an overall process by multiplying together the K values of the individual stepwise reactions that sum to make that process overall. So when I multiply here together, the KSP value of my dissolving solute from reaction 1 of 1.6 times 10 to the negative 10th times K2, which described the first of the ligand molecules being picked up by silver ion in solution, that is 2.1 times 10 to the third, and then multiplying that by the K3 for the second ligand being picked up of 8.2 times 10 to the third. The product of those three K values comes out to be an overall K value here for the total reaction of 2.7 times 10 to the negative third. Now, this is still a relatively small K, that is, a system which favors the reactant side. But that being said, it's much, much, much larger than the KSP value of our initial dissociation equation we wrote at the top there of 1.6 times 10 to the negative 10th. Implying, therefore, our solute has become orders of magnitude more soluble in a solution of ammonia than it was in a pure water solution. So now that we've calculated the K value of the overall process, on our next slide, we can now use this to understand, quantitatively speaking, why silver chloride is more soluble in a concentrated ammonia solution than it would be in pure water. Let's see that on our next slide. All right, for our last slide in this lecture here, we're going to look to see if we can quantitatively compare the solubility of silver chloride in a pure water solution versus the solubility of silver chloride in a solution which is 10 molar ammonia. And I've given you here the dissociation equation of silver chloride, AgCl, which separates apart into the silver ion, Ag positive, and the chloride ion, Cl negative. And I've also picked up from our last slide the equation which describes the formation of the diamine silver complex ion upon the addition of ammonia to silver chloride, that is AgCl, plus 2NH3 reacts to form AgNH3 1 positive, plus the chloride ion Cl negative. Now, because we are finding here solubilities, let's go ahead and start with a process we're familiar with now from our previous conversations around solubility for solving an ice table for the dissociation of the silver chloride in our pure water solution. That is our left-hand equation here. I'm going to go ahead and ice this thing here with the initial change in equilibrium concentrations. And again, recall that that silver chloride solute is a solid phase species, and as such will not be changing concentration over the process here. So I'm going to go ahead and ignore that column. And in a pure water solution, I will assume initial concentrations both of silver ion and of chloride ions of 0. Recall now, some amount of the silver chloride is going to dissolve. So if I assume that X moles per liter of my solute dissolves, for every X moles per liter of AgCl that dissolve, I would produce X moles per liter of the silver ion and X moles per liter of the chloride ion due to that 1-to-1 dissociation ratio. And as such, at equilibrium, the concentration of both silver ion and chloride ion would be X moles per liter. So we've got our ice table set up. Let's now go ahead and write a KSP expression. The KSP which governs this dissociation would be the concentration of Ag1 positive times the concentration of the chloride ion Cl1 negative. And now I'll go ahead and import from our previous slide the value of KSP which governed that dissociation, which again off the previous slide was 1.6 times 10 to the negative 10th. And now let's go ahead and import the equilibrium concentrations of these ions defined in terms of X. Both the silver ion and the chloride ion from my ice table were X moles per liter, which means therefore my KSP value would be equal to X squared. And solving here simply now yields a value of X in the system of 1.3 times 10 to the negative 5 molar. And recall again from our previous conversations, the X value in a dissociation equation is the solubility, the molar solubility of that dissolving solute. So 1.3 times 10 to the negative 5 moles of silver chloride would dissolve per liter of our solution, not a particularly soluble substance. All right. So now we've determined the solubility in pure water. Let's now determine how this is going to change solubility in a 10 molar ammonia solution. So again, we're going to go ahead and set up our ice table here. The initial change in equilibrium concentrations. The silver chloride, again, is a solid solute, and as such will not be part of our ice table, so we can ignore that. The ammonia in our system, again, was a 10 molar ammonia solution. So that value here is going to be, and under initial conditions, 10.0 molar. And again, I'm going to assume the initial concentrations of both my diamine silver complex ion and the chloride ion will both start as 0. Now again, assuming that some amount of the silver chloride dissolves, I would see a change in concentration of plus X moles per liter for both the diamine silver complex ion and the chloride ion for each silver chloride that dissolved. And I would see a change in concentration of minus 2X moles per liter for our reactant ammonia, NH3. Leaving me then with equilibrium concentrations of 10 minus 2X moles per liter for ammonia, and then X for both of the product ions. And just as we did on the other side, let's now go ahead and write our K expression. The K expression here is, in this case, the concentration of the complex ion AgNH3 positive times the concentration of the chloride ion as my products, divided by the concentration of our ammonia, NH3, which gets squared due to its coefficient in that balanced equation. And following a now familiar process, I'm now going to import the K value from our previous slide, which we had calculated that governed the dissociation of the silver chloride in the ammonia. That K value again was 2.8 times 10 to the negative third. And now importing the equilibrium concentrations defined in terms of X from our ice table into our K expression. That's going to be now both of those products, the diamine silver complex ion and the chloride ion are X, so that gives me X squared in my numerator, divided by the concentration of 10.0 minus 2X, which again gets squared in my denominator. Now at this point, I might run into a little trouble here if I were to make an assumption in this case, because again, that K value is not super small, but I can actually avoid making an assumption entirely here if I recognize that on the right side of my equation here, what I really fundamentally have is a ratio of squares, that is X squared over 10 minus 2X squared. And as such, I'm going to simplify my calculation here by simply square rooting both sides of my equation. So on the left side, I get the square root of 2.8 times 10 to the negative third is equal to, on the right side there, that is the square root of quantity x squared over 10 minus 2x squared. Simplifying that down and making some calculations here, I find that the square root of 2.8 times 10 to the negative third is approximately equal to 0.052. And then the right-hand side there, the square root of a square is just the initial thing you started with. So the square root of x squared is x, divided by the square root of 10 minus 2x quantity squared, which would just give me 10 minus 2x. And I can now simply solve algebraically from here. I'm going to multiply both sides by 10 minus 2x. That yields now an expression which is 0.52 minus 0.10x is equal to, on my right side there, I just have my x left over. Add the 0.10x to both sides, and that gives me 0.52 is equal to 1.10x. And then simply solving here, dividing by 1.10, yields an x value of approximately 0.47 molar. All right, so we did some math, and we have some numbers. Now let's think about what this means in terms of our equation. On the pure water solution, that molar solubility of the silver chloride was 1.3 times 10 to the negative fifth moles per liter. Now here in our concentrated ammonia solution, I now have a molarity of 0.47 molar for the x value, which again is the molar solubility of that dissolving solute. So it appears here that we are orders of magnitude more soluble in that concentrated ammonia solution, which should make logical sense for two clear, distinct reasons. Number one, the K value, which governs the dissociation of the solute in the ammonia, is much, much larger than the K value of the KSP for the pure water solution. So again, we would more heavily favor the formation of products and the therefore dissociated ions if we were in concentrated ammonia. And number two, remember, we are essentially using here a concentrated ammonia solution, which really then is going to push our equilibrium very far to the right according to the principles of Le Chatelier's principle. That is, an increase in concentration of ammonia should cause an increase in the rate at which the ammonia molecules bump into our solute, and as such, push that equilibrium far to the right, which again would make this more soluble as we push it towards the position of the dissociated ions in solution. So we can understand that both with a larger value of the K, and as also we have a higher concentration, which then pushes our equilibrium to the right according to Le Chatelier's principle, the silver chloride is much, much more soluble in a concentrated ammonia solution than it would be in pure water. All right, so there we have it. That is a quantitative approach to understanding complex ion equilibria. Thanks for listening, and we'll see you at the next lecture.